How do we use hybridization to explain lone pairs of electrons? Well, the easiest way to do that, or I guess, would be with ammonia. You guys remember ammonia? We've looked at this how many times now? Okay, and if we were to do a Lewis structure for ammonia, this is like the second molecule we ever did a Lewis structure for. This is what we would get. How many electron domains are around the nitrogen?
4.
4. Therefore, 4 domains. What are we going to draw? 3-dimensionally. Anytime there's 4 domains, it automatically makes us draw a tetrahedron. Okay, so we draw our tetrahedron. Boom, 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 boom. Except one of them happens to be a lone pair of electrons. Okay, so we get something that looks like this. If you remember, this is a trigonal pyramidal structure. The bond angle here is less than 109.5 degrees. It's actually around 107, but we'll let you go with that. Okay, how can this be explained? Well, there's a couple of different things we have to worry about. The lone pair of electrons for one, and that's about really the main thing we have to explain here. Now, looking at nitrogen's atomic orbital or atomic configuration. We get 2 and 3. Does everyone concur? That's what we would draw for the nitrogen electron configuration. Well, once again, we have to explain this. There's 4 domains, so we're going to need 4 hybridized orbitals. Well, once again, what we're going to do is we're going to promote this one up here. Okay? We're going to once again blend or hybridize those 4 orbitals into 4 identical sp3 hybridized orbitals. And as it turns out, one of those hybridized orbitals is going to already have a pair of electrons in it because there's 5 electrons. 1, 2, 3, 4, 5. Okay? And that is what explains the lone pair of electrons for the nitrogen. Because if I were to draw the balloon diagram for this, we would get something that looked like this. Okay, and then we would get this little area right here that had that lone pair of electrons in it. And these would be the sp3 hybridized orbitals here. And then, of course, the hydrogens are using just the 1s orbitals from the hydrogen. And there's what we have there, okay? So that explains one lone pair of electrons. Once again, 4 domains, okay? Did I go into the difference between sigma and pi bonds with you guys on 11 days ago? Yeah. Well, the answer to that question is yes, because I've already seen it on Megan's paper, and she wouldn't be making that up, I don't think, right? So I'm going to review again what a sigma bond is. Okay? And I know if you're going to write anything down, one would be the first thing I had to write down earlier today. That's the definition of hybridization. Secondly, sigma, and there's the Greek letter sigma, bond. Okay? A sigma bond is a bond formed between hybridized orbitals. It's formed between hybridized orbitals. Every covalent bond has at least one, not at least, has one sigma bond. Every hybridized, every covalent molecule bond, every covalent bond has a sigma bond. You might be thinking to yourself, well, why do we care about that? Sure, sigma bond. You'll find out here in a little bit later. All right. Now, one other, just because it's interesting, I think some of you might find it interesting. If any of you go on and take more chemistry courses in your lives, you will also find that this is helpful and useful for you. How how do we explain water? Well, once again, this might have been like the third molecule we ever did. If we were to draw a Lewis structure for water, it would look like this. How many electron domains are there? 4. Therefore, what are we going to draw? A tetrahedron. So you guys are getting this. I'm actually fairly pleased with you guys and your understanding, apparent understanding of that right now. Okay. For purposes that I feel are necessary, I'm going to go ahead and draw it this way. So what's the unique feature about the water molecule that has 4 electron domains? Well, it has 2 lone pair of electrons. How can I explain that using hybridization? Well, once again, oxygen has 6 valence electrons at the third energy or second energy level, 2 and 6. Well, guess what we're going to do? We're going to we have 4 domains, so we have to have 4 hybridized orbitals. Once again, we're going to promote this one, say up here, doesn't really matter where, okay? We're going to produce from that 4 identical sp3 hybridized orbitals, but now 2 of them are going to have unpaired electrons. The other 2 are going to have paired electrons. And through all the reasoning that we did earlier for the ammonia, this explains the 2 lone pairs of electrons around oxygen and also allows them to bond with the hydrogens. I'm not going to draw the balloon draw diagram or anything. Does that make any sense what I'm saying there? So where I'm going with this is that's how you can account for lone pairs of electrons with this idea of hybridization. All right. I can't remember, and we may not have in this class gotten to see this molecule here. Does that ring a bell from 11 days ago? Yeah, I don't think we went there. I think I did BCl3, which is awesome that you guys have that in your notes, okay? My other groups did not get that. If you guys could draw a quick Lewis structure for BCl3, or B, wow, for H2CO. This shouldn't take you long. So, anyone go anywhere out of Delaware County for spring break? Where'd you go, Todd?
Pennsylvania.
That's out of Delaware County. Where in Pennsylvania?
To Hershey and
Oh,
I went to Franklin County.
Franklin County. Ooh, nice. How about you?
South Carolina,
Where?
Charleston.
Really? I went through Charleston twice. Once on the way to Florida, once on the way back. Everett, did you say you?
Yep.
Where'd you go?
Colorado.
Really? Where there?
Fort Collins.
Was in Colorado skiing?
I went for college visits.
Oh, did you?
Yeah.
Nice.
Had family down there. So
Okay.
I stayed with them.
Right. Yep, did a quick 4-day trip to Florida. Went down, spent a couple days, came back.
By yourself?
I had a friend go with me. He had nothing else. He's bus driver for Hayes, and he had nothing else going on. And his wife's from Mexico, so I said, "Hey, want to go?" He said, "Sure, why not?" Because otherwise, it's just going to be me. All right, you guys done? How many bonds did you calculate? Nobody calculated any bonds. How many bonds did you calculate?
4.
Who said that? Excellent, 4. So boom, boom, boom. Oh, wait a minute, but I've only got 3 atoms.
Double bond.
Oh, double bond here. Awesome. Boom, 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 boom. Complete the octets. there were 10 electrons in the system, I'm hoping you guys came up with, right? And so there we go. So, how many electron domains around the carbon?
4.
3.
3. So what's that going to cause us to draw? Trigonal planar. So we're going to go boom, 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 boom. Okay. So what is different about this molecule? There's actually more than one thing. What is different about this molecule than the other 3 that we've gone through today? The ammonia, the methane, and the water.
This one has a double.
This one has a double bond. And what else is different? There's only 3 domains. Whereas the other 3 we've done today all had 4 domains and were sp3 hybridized, right? So this one only has 3 domains. How can I explain this? Well, here we go. I know this gets old. This is why I'm telling you guys not to write this stuff down. Just follow along, try to make sense of it. I know I'm going quickly, but that's because I've already covered most of this. Once again, there's carbon. Okay? Again, this bond length and these bond lengths do not match up with the distance from the nucleus that this orbital is and this orbital is. Also, these are 90 degrees apart, whereas, as you guys all know, this bond angle is 120 degrees, okay? So for a number of reasons, this does not explain this in any way. So we're going to have to hybridize some of these things. Now this time though, I only have 3 domains. So that means I only need 3 of those orbitals. So what we're going to do is, once again, promote this electron up here like we do, okay? And so, what are we going to get? We're going to get 3 identical orbitals, each with 1 electron in it, plus 1 unhybridized orbital with an electron in it. Okay, so that one just stayed the same. Nothing happened to that orbital because we only need 3 domains, 3 connections to make, right? Does anyone want to take a stab as to what we're going to call these hybridized orbitals?
SP2.
Yeah, they were formed from an S and 2 p orbitals, so we're going to call these sp2 hybridized. It's really that simple. As you're going to find out as we get towards the end of the day, all you have to do is look at how many domains there are, and then use your hand. S, go up to the number of p's until you run out of p's. In this case, we only need 3 orbitals, right? So S, 2 p's, so sp2. Anyway, so how do we explain? So now we know how we got this. Now we know how we got the 3 domains. How are we going to form this double bond? And that's the fun part. So I'm going to go ahead and draw this. Please do not waste your time doing this. There's my 3 orbitals with 1 sp2 hybridized orbitals with 1 electron in each of them. Okay? Now I've got to get these hydrogens connected on there. So I'm going to go ahead and use, once again, the hydrogen 1s orbitals and the electron that it provides to go there. Now the question is, what do I do with this and the oxygen? For reasons I'm not going to go into right now. If you'd like to discuss it at a later time with me, that's awesome, that would be great. I will tell you that the oxygen is also going to be sp2 hybridized. So I'm going to draw an oxygen over here and put its orbitals there, also sp2 hybridized. Now, as it turns out, for the reasons that I went through with the nitrogen and the oxygen in the water and the ammonia molecules, there's lone pairs of electrons sitting here and a single electron sitting there. Now, let's look where we are so far. What kind of bond is this?
Sigma,
Why?
because it's only a single bond.
Because it's formed between hybridized orbitals. okay? It's formed between hybridized orbitals, therefore it's a sigma bond. Notice something though, as you all know, carbon has 4 valence electrons. We've only accounted for 3 of them so far. Oxygen has 6 valence electrons. We've only accounted for 5 of them so far. We have forgotten so far about that unhybridized orbital. Now that's a p orbital. Does anyone remember the shape that a p orbital takes? Way back from chapter 4. That dumbbell shape, okay? So what I'm going to do is sketch in a dumbbell-shaped orbital here. So this is the 2pz orbital for carbon with 1 electron in it. As it turns out, because oxygen is also sp2 hybridized, it also has a 2pz unhybridized orbital with an electron in it. Here's where it gets fun. What happens is, to form this double bond, is these two, which one should I use here? These 2 lobes are going to overlap. Okay, they're going to kind of overlap each other and form the second bond. And here's where many students, when they first get introduced to that, like you guys right now, have a tendency to think of this as a triple bond. Is that what some of you are thinking? Okay, but here's my analogy that should work for you. You guys have eaten hot dogs before? You know, the sandwich with the bun and everything? Okay, so you've eaten a hot dog sandwich before. How many hot dogs are in there? 1. How many buns? 1. Would you agree? Now, that bun actually has 2 halves. 1 on top, 1 on the bottom. Would you agree with that? Okay, but it's 1 bond. Same thing here. This is a bond. We've already identified it as a sigma bond. This is a bond. Okay, it kind of surrounds the sigma bond. And I possibly introduced you to this because I saw it in your notes. This is called a pi bond. So, a pi bond is a bond formed between unhybridized orbitals. Oh, we already have that, don't we? Oh, you just described it. A pi bond is formed from unhybridized orbitals. So I'm going to get a chance to go over this in more detail here in a couple minutes, but I'm going to re-emphasize. A sigma bond is formed between hybridized orbitals. Every bond has 1 sigma bond. If there's any more bonds, in this case a double bond, one of them is going to be a sigma bond. The other one's going to have to be a pi bond formed between unhybridized orbitals. That's how you explain double bond. Cool, huh? You can see you're just immensely thrilled. Yes?
Is a hot dog a sandwich?
Sure, what else is it?
Well, I thought that's just like.
Okay, have you ever had peanut butter and jelly? Is that a peanut butter and jelly sandwich?
Yeah.
Great. What was in it? Peanut butter and jelly and
Well, like
bread. Have
two
you ever had a
pieces of
hamburger
bread.
sandwich?
I know, I call that hamburger.
I know, but if you go to a restaurant, it's under the category sandwiches.
No, it's usually, it has its own category.
Yeah, I'm pretty sure so.
Anyway, yes, it's a sandwich. You know why it's a sandwich? Because it has a bun.
Well, usually sandwiches have like a
Bun.
piece of bread and then another piece of bread.
What's a bun?
A piece of bread. But like
And a
two
Here we go. Remember, this is all going to be for the world to see, this conversation. All right, moving on. So should I say your name? Where I'm going with this now is you currently have seen 2 examples of sp2 hybridization. The one we walked through on Thursday was BCL3. The one we just walked through right there was HTCO. So, and I see probably most of you already have on your little geometry charts, again, across from 3 electron domains, you already have SP2 written, you're good. You guys already did that probably, because that's what we did on Thursday. So now I have caught us up to where we left off on Thursday with a couple of little additions to that, with the lone pairs of electrons and the double bond. Next, if you guys could draw a quick Lewis structure for this molecule. So Morgan, you said you didn't leave Delaware County. Oh. Is the weather still nice there? Because you were still there, weren't you? Where in Florida? Me too. Were you with the band? Yeah, I left before you got there. You guys got there on what, Tuesday? I got home at 4 a.m. on Tuesday. See? We must have left at about the same time then, huh?
How long was the drive?
Depends on how many times I stop. Oh yeah. 15.
Did you like drive the whole thing?
Yeah.
One leg?
That's what you do. Just go.
Fill up on coffee?
Huh?
Fill up on coffee, just go?
Oh yeah, just go. What? St. Louis and back. I mean, it's the same thing. I've done that before too. Yep, left Thursday after school, got there Friday afternoon. Well, actually, no, I didn't leave Thursday after school. I left Thursday at 10:30 at night. Yeah, because I don't, I'll tell you what, driving at night, it's just you and the semis. But you can just go. Yeah. I much prefer driving at night.
Just take a little nap after school?
Yes. And then got up Monday morning and said goodbye to my son as he went to work and took off. All right, you guys got this? How many bonds? Yep. Okay, 5 bonds. Ooh, this must be an exception because there's only 4 atoms.
The C comes at triple bond.
Oh, we forgot about that, yep. Triple bond, there we go. 10 electrons in the system, we calculated 5 bonds, we used up all 10 electrons. Okay, so there we go. Now, I'm hoping most of you can understand that by examining this carbon, whatever we come up with for this carbon is going to be exactly the same as this carbon. Same scenario, right? So let's just look at this carbon for now. How can I, well, first of all, how many domains around that carbon? 2. So what sort of geometry is this? Linear, okay. And what's the bond angle here? 180. I mean, it's all the same stuff we've done before. It's a linear molecule, okay. 2 things. How can I explain a linear molecule or 2 domains for a carbon? And how do I explain a triple bond? Well, we now have all the pieces. This will go fairly quickly. Please, I highly, highly recommend not drawing anything that I'm about to draw. Please just pay attention, try to make sense of it, okay? Because the drawing is going to be so ugly by the time it's all done that if you were to go back 5 days later and look at that drawing, you would have no idea why you drew all these little lines, okay? So just please try and pay attention to what's going on. All right, once again, we have to come up with 2 domains. Well, if that's the case, I only need 2 orbitals. So, we're going to blend two of those together, or hybridize two of them, and we're going to leave the other ones remaining. We're going to go ahead and pop this one up here like we've been doing all this time. Boom, 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 boom. Anyone want to take a stab as to what we're going to call these two hybridized orbitals? S and P. So these are SP hybridized. This is still the unhybridized 2py, 2pz. Okay, so how can I explain this carbon? Well, here we go. Here's an SP orbital. There's an SP orbital. Electron, electron. Now, let's go ahead and throw the hydrogen in there just for fun. Hydrogen 1s with its electron. Now, as it turns out, we have another carbon. Let's go with some pacer colors here. This carbon is also going to be SP hybridized for all the same reasons that we said it was going to be with its electron. What kind of bond is this? A sigma bond, because it's formed between hybridized orbitals. Okay? We also have another SP hybridized orbital over here. Boom, boom. Let's throw that other hydrogen in here with its electron. Okay, so there we go. We have all the connections between the atoms. What we don't have are those. So I've currently used up these two electrons. One was here, one was here. So far, so good? But I've got two electrons in two different unhybridized orbitals. Now remember, those are 90 degrees apart relative to each other. So I'm going to draw one of them here. We'll call this one the 2py. And I'm going to draw another one 90 degrees away from that, or the 2pz with the electron there. Okay, so there's the two unhybridized orbitals. Same thing can be done for this carbon. Okay? Anyone want to take a stab as to what's going to happen now? What happened with the double bond? Go ahead. They're going to do this. They're going to overlap. That's the word you were looking for. So, these two are going to overlap each other since they're in the same plane, the 2py's, and the 2pz's are also going to overlap each other. Now, I'm sure most of you have never done this before, but this would be like having a hot dog with two buns, okay? Top and the bottom, each of the sides. That is how a triple bond is formed. So I'm going to ask this very carefully. We're going to look at this drawing first. How many sigma bonds between here and here? One. That's all there ever is. How many pi bonds? Two, because there's two different unhybridized orbitals. So anytime you look at a bond, there's always going to be a sigma bond, and if there's more than one bond, the other ones are always going to be pi bonds. Are you following? Okay. So if I were to look at this molecule and ask you, how many sigma bonds, what would you tell me? How many connections between different atoms are there? Is that a connection between two different atoms? Sigma bond. Is this a connection between two different atoms? Sigma bond. Is this a connection between two different atoms? Sigma bond. How many sigma bonds? 3. How many pi bonds? 2. Because anything other than a single bond is a pi bond. So 3 sigma, 2 pi. Okay. Let's try to pull all this together. Now, by the way, that is how you come up with SP hybridization. Anytime you have two domains, it's SP hybridized. You can go ahead and add that to your chart if you haven't already done so. 2 electron domains is going to be SP hybridization. Now, you'll notice that we still have 2 sets of domains that we haven't covered yet. The 5 domains and the 6 domains, right? Your first answer that comes into your head is wrong. So ignore that. But does anyone want to take a stab as to what types of hybridization a 5 domain would be? Sean, the first thing that pops into your head is wrong.
I got it. SP3D.
Yes! Now, was the first thing that popped into your head wrong?
Yeah.
Because he was going to say SP, right? How many else were you thinking SP4? Yeah, see? First one's wrong. Good, Sean. I have confidence in you. But that's exactly right. SP3D. Because remember, to get to 5 domains, that's when we're talking third period inhibitor elements that utilizes the d orbital for the extra electrons. Here we go. What about 6 domains? SP3D2. SP3D2. I am not going to go into that whole thing with those because I think you guys see the picture now. Okay? So, here we go. 2 domains. Obviously, on the paper you have SP hybridized. 3 domains are going to be SP2, 4 domains SP3, 5 domains SP3D, and 6 domains SP32. Now, could I have just told you guys, make a column, put SP for the top one, SP2, and said memorize that? I could have, but you would have no idea what that meant. And so hopefully now, for those of you that go on and take another chemistry course in your life, which some of you will, believe it or not, this will become in very handy, the fact that you've actually been presented this information before. Believe it or not, it does come back, if you look at it. All right, I should have like 3 minutes left. How much? 1? Darn it, I was going to have you guys try 1. You're right. Okay. Well, that's right. I've got all kinds of fun for you tomorrow. We are nearly done, people.